Why is the universe so quiet? With hundreds of billions of stars in our galaxy alone, we should be drowning in alien radio signals, stumbling across ancient megastructures, watching interstellar civilizations spread across the cosmos. Instead, we've found nothing. Tonight, we're confronting the most unsettling question in science. Are we truly alone, or is something else going on? And here is a question for you. What's the first question you'd ask an alien civilization if we made contact with them tomorrow? Let me know in the comments. I will pin the most creative answer. Now let's begin. The question we're tackling isn't new. Back in 1950, a brilliant physicist named Enrico Fermi was having lunch with some colleagues at Los Alamos National Laboratory. They were chatting about flying saucers and the possibility of alien life when Fermi suddenly stopped and asked a simple question that would echo through the decades. Where is everybody? Those 4 words captured what we now call the Fermi paradox. It's the contradiction between the high probability that alien civilizations should exist and the complete absence of evidence that they do. Think about it for a moment. Our Sun is just one ordinary star in the Milky Way. It's not special, not particularly large or bright. It formed about 4.5 billion years ago from a cloud of gas and dust left over from previous generations of stars. If life could arise here on Earth, why wouldn't it emerge on countless other worlds orbiting similar stars throughout the galaxy? The mathematics behind this question are staggering. Scientists use something called the Drake equation, formulated by astronomer Frank Drake in 1961, to estimate how many intelligent civilizations might exist in our galaxy. The equation considers factors like the rate of star formation, the fraction of stars with planets, how many planets per star system might be habitable, and what percentage of those might actually develop life. Recent discoveries from missions like Kepler and TESS have given us much better numbers for some of these variables. We now know that planets are incredibly common. Nearly every star you see in the night sky likely hosts at least one planet. Research published in 2020 using Kepler data suggests that roughly half of Sun-like stars have a planet in their habitable zone. That's a massive number when you consider how many stars exist in our galaxy alone. Let's put this in perspective. Imagine you're standing on a beach and every grain of sand represents a star. The number of stars in the observable universe exceeds the number of grains of sand on all the beaches on Earth. Now imagine that even a tiny fraction of those stars have planets where life could potentially emerge. The numbers become almost incomprehensible. Estimates suggest there could be as many as 300 million potentially habitable worlds just in the Milky Way. And that's just our galaxy. The observable universe contains approximately 2 trillion galaxies. The scale is beyond anything our minds evolved to grasp. But here's where things get really interesting. Our Sun and Earth aren't special in another crucial way. They're relatively young compared to the age of the universe. The cosmos is about 13.8 billion years old. Our Sun formed when the universe was already 9 billion years old. That means there was a vast stretch of time, billions of years, when other star systems could have formed and potentially given rise to intelligent life. Some civilizations could have had a head start of millions or even billions of years. Imagine what a civilization could accomplish with just 1 million years of technological development beyond where we are now. We went from the first powered flight at Kitty Hawk in 1903 to landing on the moon in 1969. That's just 66 years. What might we achieve in 1,000 years? 1 million? 1 billion? Here's where the paradox truly bites. Even traveling at speeds far slower than the speed of light, a civilization could theoretically colonize the entire galaxy in just a few million years. Computer models show that even with technology only slightly more advanced than what we have today, interstellar travel is feasible. It would be slow and require generational ships or some form of suspended animation, but it's not impossible. Some scientists have proposed that advanced civilizations might send out self-replicating probes that could explore and potentially colonize star systems, then build copies of themselves to continue the exploration. This approach, inspired by mathematician John von Neumann, could allow a civilization to spread throughout the galaxy relatively quickly on cosmic timescales. The Milky Way is approximately 100,000 light-years across. If a civilization sent out ships traveling at just 10% the speed of light, and those ships stopped to build new ships every 1,000 years or so, they could reach every corner of the galaxy in less than 1,000,000 years. That sounds like a long time to us, but remember, our galaxy is over 13 billion years old. 1,000,000 years is nothing, barely a cosmic blink. So if it's so easy, where are they? Why hasn't anyone done it? Why haven't we detected even a single sign of intelligence out there in the vast darkness? This brings us to one of the most exciting developments in modern astronomy. In the last 3 decades, we've gone from knowing of exactly 0 planets beyond our solar system to confirming over 5,000 exoplanets. The Kepler Space Telescope, launched in 2009, revolutionized our understanding by staring at a single patch of sky and watching for the tiny dips in starlight that occur when a planet passes in front of its star. This method, called the transit technique, allowed scientists to discover thousands of new worlds. Some are scorching hot Jupiters, massive gas giants orbiting closer to their stars than Mercury orbits our Sun. Others are frozen ice worlds far from any warmth. But crucially, many sit in that sweet spot we call the habitable zone. The habitable zone is the region around a star where conditions might be just right for liquid water to exist on a planet's surface. Not too hot that water boils away into space. Not too cold that it freezes solid forever. Just right, like in the story of Goldilocks. Water is essential for life as we know it. It's an incredible solvent, meaning it can dissolve and transport nutrients. It remains liquid over a wide temperature range, and it has unique properties that make it perfect for the chemistry of life. Every living thing on Earth, from the smallest bacteria to the largest whale, requires water to survive. So when astronomers search for potentially habitable worlds, they first look for planets in the habitable zone. Recent studies have refined our understanding of these zones. It's not enough for a planet to simply be the right distance from its star. The planet needs to have the right mass to hold on to an atmosphere. It probably needs plate tectonics to recycle carbon and regulate temperature over geological timescales. It might need a large moon to stabilize its axial tilt and create stable seasons. It potentially needs a Jupiter-like planet in the outer solar system to act as a gravitational shield, deflecting dangerous comets and asteroids. Earth has all these things, and for a long time, scientists wondered if that made us incredibly rare. But as we discover more and more exoplanets and learn more about their properties, we're finding that Earth-like worlds might not be as uncommon as we once thought. If you're enjoying this deep dive into one of science's greatest mysteries, this would be a perfect moment to hit that subscribe button and give this video a thumbs up. It truly helps the channel grow and allows me to keep bringing you fascinating content about the cosmos. Your support means everything as I build this community of curious minds exploring the universe together. In 2014, NASA announced the discovery of Kepler-4 152b, a planet roughly 60% larger than Earth orbiting in the habitable zone of a Sun-like star. The planet takes 385 days to complete one orbit, remarkably similar to Earth's year. It's located about 1,400 light-years away in the constellation Cygnus. While we can't yet determine if it has water or an atmosphere, the discovery showed us that Earth-sized worlds in habitable zones around Sun-like stars actually exist. More recently, in 2025, astronomers announced the detection of what they're calling the first Earth cousin, a world so similar to our own in size, temperature, and orbital characteristics that it represents our closest analogue yet discovered. These findings have profound implications for the Fermi paradox. Let's talk about SETI, the search for extraterrestrial intelligence. Since 1960, scientists have been using radio telescopes to listen for signals from alien civilizations. The logic is straightforward. Radio waves travel at the speed of light and can cross vast interstellar distances without being absorbed or scattered too much by dust and gas. If an alien civilization wanted to announce its presence, or if we simply detected their routine communications leaking into space, radio would be a logical medium. We've been broadcasting radio and television signals into space since the early 20th century. Those signals form an expanding bubble around Earth, now stretching roughly 125 light-years in all directions. Any civilization within that bubble with sensitive enough equipment could detect us. But despite decades of searching, despite listening to millions of radio channels across thousands of star systems, SETI has found nothing, not a single confirmed artificial signal. The silence is deafening. There was one famous exception, a signal detected on August 15, 1977, by the Big Ear radio telescope at Ohio State University. The signal was so strong and so unusual that astronomer Jerry Amon circled it on the computer printout and wrote "Wow" in the margin. The wow signal lasted 72 seconds and appeared to come from the direction of the constellation Sagittarius. Despite numerous attempts to detect it again, it has never repeated. We still don't know what caused it. It remains one of astronomy's most tantalizing mysteries, but without confirmation or repetition, we can't claim it as proof of alien intelligence. Modern SETI efforts have expanded beyond just radio. Scientists are now looking for optical signals, brief flashes of laser light that an alien civilization might use for communication or even propulsion. They're searching for technosignatures, evidence of advanced technology like massive engineering projects that might block out starlight in unusual patterns. The Breakthrough Listen initiative, funded by entrepreneur Yuri Milner and launched in 2015, represents the most comprehensive search ever undertaken. Using some of the world's most powerful telescopes, it's surveying 1 million nearby stars, the entire galactic plane, and even 100 nearby galaxies. The project is examining 10 times more sky than previous programs and is sensitive to signals far weaker than any we could currently detect. Yet the silence continues. This brings us to possible solutions to the Fermi paradox, and there are dozens of them, each more thought-provoking than the last. Let's explore some of the most compelling explanations scientists have proposed. The first category involves what we might call the "we're special" hypotheses. Maybe Earth really is extraordinarily rare. This is known as the rare Earth hypothesis, proposed by paleontologist Peter Ward and astronomer Donald Brownlee in 2000. They argue that while simple microbial life might be common in the universe, complex multicellular life is incredibly rare. Earth had to meet so many specific conditions for complex life to evolve. We needed to be in the right location in the galaxy, not too close to the chaotic center where supernovae and radiation would sterilize planets regularly, but not too far out in the sparse outer regions where heavy elements necessary for life are scarce. Our sun had to be the right size. Larger stars burn too hot and die too quickly for complex life to evolve. Smaller stars live longer but emit less energy and tend to have violent stellar flares that could strip away planetary atmospheres. We needed Jupiter's gravitational influence to protect us from comet bombardments, but not so close that its gravity would destabilize Earth's orbit. We needed a large moon to stabilize Earth's axial tilt, preventing wild climate swings that might prevent complex life from gaining a foothold. We needed plate tectonics to recycle carbon and create a thermostat that keeps Earth's temperature relatively stable over billions of years. The list goes on and on. When you multiply all these probabilities together, maybe habitable planets with complex life become vanishingly rare. But here's a counter-argument that's equally compelling. Life appeared on Earth remarkably quickly. The planet formed about 4.5 billion years ago. It spent its early years being bombarded by asteroids and comets, with conditions far too violent for life to survive. Yet by 3.5 billion years ago, possibly even earlier, we find evidence of life in the geological record. That means life emerged within a few 100 million years of Earth, becoming even marginally habitable. In cosmic terms, that's incredibly fast. If life arises that quickly whenever conditions permit, it suggests that the emergence of life isn't the bottleneck. Maybe life is common, but intelligence is rare. This leads us to another fascinating possibility known as the Great Filter. Imagine there's a step in the evolution from non-living matter to a galaxy-spanning civilization that's incredibly difficult to pass. This is the filter. Very few make it through. The terrifying question is, where is this filter? Is it behind us or ahead of us? If it's behind us, maybe the jump from non-life to life is extraordinarily rare. Or perhaps the evolution from single-celled organisms to multicellular life is the nearly impossible step. On Earth, single-celled life existed for billions of years before multicellular organisms appeared. Maybe that's the bottleneck, and we're incredibly lucky to have passed it. If that's true, the galaxy might be teeming with microbial life, but devoid of anything more complex. But what if the Great Filter is ahead of us? That's a chilling thought. Maybe civilizations inevitably develop technologies that lead to their own destruction before they can spread across the stars. Nuclear weapons, artificial intelligence, engineered pandemics, climate catastrophe, nanotechnology run amok. Perhaps there's something about reaching a certain level of technological sophistication that carries with it the seeds of extinction. Every civilization reaches a point where they develop the means to destroy themselves, and very few navigate that danger successfully. If that's true, the silence we hear might be a warning. The galaxy might be filled with the ruins of civilizations that didn't make it through their own adolescence. Speaking of vast distances, if you've ever wondered about the incredible challenges of interstellar travel, I actually made a video exploring exactly how long it would take to reach Andromeda, our nearest major galactic neighbor, using various propulsion methods we've theorized or developed. It really puts into perspective just how isolated we might be in this cosmic ocean. Check it out after this video if you're curious about the practical realities of crossing those mind-bending distances. The link is in the description and on the card above. There's another category of explanations that's even stranger. Maybe aliens exist, but we can't see them because we're not looking in the right way or at the right time. This is sometimes called the "they're here, but we can't detect them" hypothesis. Consider how different civilizations might be from us. We're looking for radio signals because that's the technology we use. But what if advanced civilizations communicate in ways we can't even imagine? What if they use quantum entanglement, gravitational waves, or some physics we haven't discovered yet? We'd be like someone trying to detect Wi-Fi signals using only their ears. The technology is all around us, but we lack the sensors to perceive it. There's also the zoo hypothesis, which suggests that alien civilizations know we're here, but have deliberately chosen not to contact us. Perhaps there's a galactic equivalent of Star Trek's Prime Directive, a rule that says advanced civilizations shouldn't interfere with less developed ones. Maybe they're waiting for us to reach a certain level of technological or social maturity before revealing themselves. Or perhaps they're studying us the way we might observe animals in a nature preserve, careful not to disturb the natural evolution of our civilization. It's a humbling thought, isn't it? The idea that we might be a protected species observed from afar by intelligences we can't even detect. Then there's the simulation hypothesis, which pushes things into truly mind-bending territory. What if we're living in a computer simulation created by an advanced civilization? In that case, the universe we observe might be deliberately constrained. The simulators might have chosen not to include other intelligent life in our observable region, either to simplify the simulation or to see how we develop in isolation. Before you dismiss this as science fiction, consider that many serious physicists and philosophers, including Nick Bostrom at Oxford University, have argued that if civilizations can create realistic simulations of conscious beings, and if they create many such simulations, then statistically we're more likely to be living in a simulation than in base reality. It's a strange loop of logic, but it's harder to refute than you might think. Another intriguing possibility involves the nature of intelligence itself. Maybe there's something about the way intelligence evolves that makes civilizations turn inward rather than outward. Think about our own trajectory. We're increasingly living in virtual worlds, spending time in digital spaces rather than exploring physical ones. What if every civilization reaches a point where virtual reality becomes so sophisticated and satisfying that they lose interest in expensive, dangerous physical exploration? Why send ships to distant stars when you can create entire universes inside computers? Why risk the hazards of space travel when you can explore infinite simulated worlds from the comfort of your home planet? Advanced civilizations might become contemplative rather than expansionist, focusing their energy on art, philosophy, virtual experiences, and inner exploration rather than outer conquest. There's also the possibility that we're simply too early. The universe is 13.8 billion years old, but it wasn't always hospitable to life. The first stars contained almost no heavy elements, just hydrogen and helium from the Big Bang. Carbon, nitrogen, oxygen, iron, all the elements essential for life as we know it had to be forged in the cores of stars and scattered through space when those stars exploded. It took several generations of stars living and dying to enrich the galaxy with enough heavy elements for rocky planets and complex chemistry to be possible. Some cosmologists argue that we might be among the first civilizations to emerge in the universe. The cosmic dawn of intelligence might just be beginning. If that's true, the galaxy isn't silent because everyone is dead or hiding. It's silent because we're the pioneers, the first to look up and ask where everyone is. But let me share something that might be the most sobering explanation of all. It's called the sustainability filter, and it's becoming increasingly relevant as we face our own challenges here on Earth. The idea is simple but profound. Maybe the problem isn't that civilizations destroy themselves quickly with nuclear war or some catastrophic technology. Maybe the problem is more subtle. Perhaps every civilization eventually faces resource limitations, climate instability, or environmental degradation. Those that don't solve these problems in time collapse before they ever reach the stars. Those that do solve them transition to sustainable, steady-state societies that don't have the excess resources or motivation for expensive interstellar expansion. Either way, galaxy-spanning civilizations never emerge. Think about the energy requirements for interstellar travel. They're enormous. To accelerate even a small spacecraft to a significant fraction of light speed requires more energy than our entire civilization currently produces. The Breakthrough Starshot initiative, announced in 2016, aims to send tiny lightweight probes to Alpha Centauri using powerful lasers to push light sails. Even these tiny craft, weighing just a few grams, would require a laser array generating about 100 gigawatts of power, roughly the output of 100 nuclear power plants, firing continuously for several minutes. And that's just to send a tiny probe on a one-way trip to our nearest stellar neighbor. Imagine the energy needed for a crewed mission or a self-sustaining colony ship. A civilization capable of such feats would need to be what physicist Kardashev called a Type II civilization on his scale of technological advancement. He proposed this scale in 1964 to categorize civilizations based on their energy usage. A Type 1 civilization can harness all the energy available on its home planet. We're not quite there yet. We're currently around 0.7 on the Kardashev scale, able to use a fraction of Earth's available energy. A Type 2 civilization can harness all the energy output of its star, perhaps by constructing a Dyson sphere, a megastructure that surrounds the star and captures its light. A Type 3 civilization can harness the energy of an entire galaxy. These classifications help us think about what advanced civilizations might look like and how we might detect them. Interestingly, we've been searching for evidence of such megastructures. In 2015, astronomer Tabitha Boyajian discovered a star, KIC 84628552, later nicknamed Tabby's star, that showed bizarre dimming patterns unlike anything seen before. The star would dim by up to 22% at irregular intervals, far more than a planet could explain. One hypothesis was that we might be seeing a partially constructed Dyson sphere or some other alien megastructure. The discovery generated enormous excitement. However, subsequent observations suggested the dimming was more likely caused by a cloud of dust or debris, possibly from a disintegrated comet. Still, the search continues. Astronomers are now systematically looking for similar anomalies that might indicate astroengineering projects. The distances involved in interstellar travel present another profound challenge. Alpha Centauri, our nearest stellar neighbor, is about 4.37 light-years away. That's roughly 41 trillion kilometers or 25 trillion miles. The fastest human-made object ever, the Parker Solar Probe, reaches speeds of about 190 kilometers per second at its closest approach to the Sun. At that speed, it would still take over 6,700 years to reach Alpha Centauri. Even if we could travel at 1% the speed of light, a speed we're nowhere near achieving, the journey would take over 400 years. Most human lifetimes would pass before the ship reached its destination. This creates enormous practical problems. How do you maintain a ship and a society for centuries? How do you ensure the descendants of the original crew will still want to complete the mission? Some scientists have proposed generation ships, massive vessels that function as self-contained worlds, where multiple generations would be born, live, and die during the journey. Others suggest suspended animation or cryogenic freezing, though we're far from having that technology. There's also the concept of seed ships, vessels that carry frozen embryos and artificial wombs, with AI systems that would raise the children upon arrival. Each solution creates its own ethical and practical dilemmas. Would it be right to conceive children who have no choice but to live their entire lives on a spaceship? What happens if the society on the ship evolves differently from Earth and decides not to complete the mission? These aren't just engineering problems. They're profound questions about human nature and purpose. Perhaps this is why we don't see evidence of widespread colonization. The barriers aren't just technological, they're biological, psychological, and philosophical. A species that evolves on a planet's surface, shaped by its gravity, atmosphere, and ecosystem, might find it extraordinarily difficult to truly leave home. We think of space travel as humanity's destiny, but that belief might be unique to us, or to our current moment in history. Other civilizations might reach the stars and decide it's not worth the cost. They might find meaning and fulfillment in ways that don't require spreading across the galaxy. Let's consider another fascinating angle that scientists are increasingly taking seriously. What if life itself is common, but technological civilizations are incredibly brief? We've been a technological civilization for perhaps 200 years, at most, depending on how you define it. That's nothing compared to the 4.5 billion-year history of Earth, or the hundreds of millions of years that complex life has existed on our planet. Dinosaurs dominated Earth for approximately 165 million years, yet they never developed technology. They never built cities, wrote books, or sent radio signals into space. What if that's the norm? What if intelligence is common but technology is a rare accident? Consider the specific circumstances that led to human technology. We're primates with opposable thumbs and complex social structures. We evolved on a world with accessible metals near the surface, fossil fuels we could use for energy, and an atmosphere that allows fire. We had the right combination of environmental pressures and opportunities that pushed us toward tool use and abstract thinking. Our brains nearly tripled in size over the last 2 million years, an incredibly rapid evolutionary change driven by factors we still don't fully understand. Maybe that combination of circumstances is rare. Maybe the universe is filled with intelligent creatures, conscious beings who experience joy and suffering, who communicate and cooperate, but who never develop technology in the way we have. Dolphins and whales have large, complex brains. They communicate with sophisticated vocalizations. They have rich social lives and even cultural traditions passed down through generations. But they'll never build radio telescopes because they live in water and lack appendages for manipulating tools. Octopuses are remarkably intelligent, capable of solving complex puzzles and displaying individual personalities. But they're solitary, they die after reproducing, and they can't pass knowledge between generations. Intelligence alone isn't enough. You need the right kind of intelligence in the right kind of body, in the right kind of environment, with the right evolutionary pressures, pushing you toward cumulative cultural knowledge. Even if a species develops technology, how long does it last? Human civilization is facing multiple existential risks right now. Climate change is altering our planet's systems faster than many species can adapt. We've developed nuclear weapons capable of destroying our civilization many times over. We're creating artificial intelligence systems whose long-term impacts we can't fully predict. We're depleting critical resources, losing biodiversity at an alarming rate, and dealing with social and political tensions that could spiral into catastrophe. And we've only had advanced technology for about a century. What will the next century bring? Will we navigate these challenges successfully, or are we approaching our own great filter? This might be the answer to the Fermi paradox. Maybe technological civilizations typically last only a few hundred years before something goes wrong. In that case, the galaxy could have been home to thousands or even millions of civilizations over its history, but they're separated by vast gulfs of space and time. They rise, they fall, and the evidence of their existence is erased by geological processes, stellar evolution, or the simple passage of eons. Two civilizations might exist in the same region of the galaxy, but be separated by millions of years, like ships passing in the cosmic night, never aware of each other's existence. There's also the question of what we're actually looking for. When we search for alien intelligence, we're largely searching for civilizations similar to ourselves, ones that use radio technology, build large structures, and expand outward. But that's based on our own limited experience. We have exactly one example of a technological civilization: us. Drawing conclusions from a sample size of one is notoriously unreliable. What if intelligence usually takes forms we wouldn't recognize? What if consciousness can exist in substrates we've never imagined? Science fiction has explored this idea extensively. What if intelligence could emerge in the plasma of a star's corona, in the quantum states of interstellar dust, or in the complex dynamics of a planet's magnetic field? What if some civilizations upload themselves into vast computer networks and exist as pure information? What if others manipulate space-time itself, existing in dimensions we can't perceive? These ideas might sound far-fetched, but they're worth considering. After all, a few hundred years ago, the idea that you could send messages instantly across the world using invisible electromagnetic waves would have seemed like magic. Our descendants 1,000 years from now might view our current searches for alien life the way we view ancient people looking for gods in the sky, sincere but fundamentally misconceived. Let me share something that gives me goosebumps every time I think about it. In 1977, NASA launched Voyager 1 and Voyager 2, two spacecraft designed to explore the outer planets. After completing their primary missions, they continued outward, becoming the first human-made objects to enter interstellar space. Each carries a golden record, a phonograph containing sounds and images selected to portray the diversity of life and culture on Earth. The record includes greetings in 55 languages, music from different cultures, and 116 images encoded in analog form. It's a message in a bottle, cast into the cosmic ocean. Voyager 1 is now over 24 billion kilometers from Earth, traveling at about 17 kilometers per second relative to the Sun. At that speed, it would take about 73,000 years to reach the distance of the nearest star if it were headed that way, which it isn't. The golden record will last billions of years in the vacuum of space, long after Earth itself might be gone. But the odds of it ever being found by an alien civilization are vanishingly small. Space is so vast, and the voyagers are so tiny. It's like placing a grain of sand in the Sahara Desert and hoping someone will stumble across that specific grain. Yet we sent it anyway because it represents something profound about human nature. We want to reach out. We want to be known. We want to say we were here, we existed, we wondered about you. That impulse, that deep desire to connect across the cosmic void might be universal, or it might be uniquely human. We don't know, but it speaks to why the Fermi paradox matters so much. It's not just an academic puzzle, it's a question about loneliness and meaning. Are we alone in experiencing the universe, in contemplating beauty, in asking why? Or are there others out there perhaps asking the same questions, feeling the same longing? Recent developments in astrobiology have given us new ways to search for life. We're no longer limited to listening for radio signals. Scientists are now looking for biosignatures, chemical indicators of life in the atmospheres of exoplanets. When starlight passes through a planet's atmosphere on its way to Earth, the gases in that atmosphere absorb specific wavelengths of light. By analyzing the spectrum, the rainbow of colors, we can determine what chemicals are present. Oxygen, methane, water vapor, ozone. Each has a distinctive spectral fingerprint. The presence of oxygen is particularly interesting. Oxygen is highly reactive. It combines with other elements readily. If you have a lot of free oxygen in an atmosphere, something must be continuously producing it to replace what's lost to chemical reactions. On Earth, that something is life. Plants, algae, and cyanobacteria produce oxygen through photosynthesis. Without life constantly replenishing it, Earth's oxygen would disappear in a few million years, combined with iron, carbon, and other elements. So finding oxygen in another planet's atmosphere would be a strong hint that life might be present. But we have to be careful. Science demands skepticism and rigorous testing. Oxygen can be produced through non-biological processes too. Ultraviolet light from a star can split water molecules into hydrogen and oxygen. The light hydrogen might escape into space, leaving oxygen behind. We need to look for combinations of gases that would be hard to explain without biology. Oxygen together with methane, for example, is highly suggestive. These gases react with each other, so finding them both in significant quantities suggests they're being continuously replenished by some active process, possibly life. The James Webb Space Telescope, launched on December 25, 2021, has revolutionized our ability to study exoplanet atmospheres. With its enormous mirror and sensitive infrared instruments, Webb can detect the faint signatures of molecules in distant planetary atmospheres with unprecedented precision. In 2023, it analyzed the atmosphere of K218b, a planet about 8.6 times Earth's mass, orbiting a red dwarf star 120 light-years away. The observations revealed the presence of carbon dioxide and methane, and possibly dimethyl sulfide, a molecule that on Earth is only produced by life, specifically by marine phytoplankton. The findings are still being debated and require confirmation, but they represent exactly the kind of discovery that could eventually answer whether we're alone. Imagine the moment when we definitively detect life on another world. It might not be intelligent life, it probably won't be. Most likely, our first detection will be microbes, simple organisms just trying to survive and reproduce, but the implications would be staggering. If life arose independently on two worlds in the same stellar neighborhood, it would suggest that life is common in the universe. The probability calculations would shift dramatically. We'd go from wondering if life is rare to assuming it's everywhere. And if microbial life is everywhere, what about complex life? What about intelligence? This brings us to something called the Copernican principle, named after Nicholas Copernicus, who in the 16th century argued that Earth wasn't the center of the universe. The principle states that we shouldn't assume we're special or privileged observers. We're probably typical. Our location in space is probably typical. Our point in time is probably typical. If that's true, and if we exist, then creatures like us probably exist elsewhere. The universe has been running the same experiment, combining atoms under various conditions, for nearly 14 billion years across trillions of star systems. The idea that it only worked once, here on Earth, seems statistically unlikely. Yet here we are, alone as far as we can tell, with no confirmed evidence of life anywhere else. This is what makes the Fermi paradox so maddening. The statistics say life should be common. The physics says interstellar travel is difficult, but not impossible. The observations say nobody's out there, or at least nobody's making themselves obvious. Something in our reasoning must be wrong, but we don't know what. Let's talk about timescales again, because they're crucial to understanding this puzzle. The universe is 13.8 billion years old. Earth formed 4.54 billion years ago. The oldest evidence of life on Earth dates back at least 3.5 billion years, possibly more. For most of Earth's history, life was microscopic. Complex multicellular life only appeared around 600 million years ago. Dinosaurs dominated from about 230 million years ago until their extinction 66 million years ago. Modern humans, Homo sapiens, have existed for only about 300,000 years. Civilization, agriculture, cities, writing all emerged within the last 10,000 years. Industrial technology is less than 300 years old. Radio technology is about 125 years old. Think about those timescales. If aliens visited Earth 67 million years ago, they would have found dinosaurs, not humans. If they visited 200 million years ago, they would have found a world dominated by reptiles and early mammals, with no hint that intelligent life would someday emerge. If they visited 500 million years ago, they would have found oceans full of strange creatures but empty continents. If they decided to check back every million years, they might have stopped by dozens of times without ever encountering anything resembling human civilization. We're so new, such a brief flicker in cosmic history. Maybe the aliens came and went long before we existed. Maybe they'll arrive long after we're gone. This is sometimes called the time coordination problem. Even if civilizations are common, they need to exist at the same time and be close enough to detect or visit each other. Imagine the galaxy as a vast ocean and civilizations as ships crossing it. If those ships appear at random times and travel relatively short distances before sinking, most will never encounter another vessel. The ocean might have hosted thousands of ships over the centuries, but they're separated by time and distance. The silence we observe might not mean we're alone. It might just mean we're temporarily isolated, living in a period when our nearest neighbors either haven't emerged yet or have already disappeared. There's another temporal factor to consider. The signals we're looking for travel at the speed of light. That's fast by human standards, but slow on cosmic scales. Light takes 8 minutes to travel from the Sun to Earth. It takes about 4 years to reach Alpha Centauri. It takes over 2.5 million years to reach the Andromeda Galaxy. If a civilization in Andromeda started broadcasting radio signals when our Australopithecine ancestors were first walking upright on the African savanna, those signals would just be reaching Earth now, and our return message would take another 2.5 million years to get back to them. Any conversation would span epochs of evolutionary time. Species would rise and fall in the gaps between messages. Even within our own galaxy, the light speed delay creates challenges. The Milky Way is roughly 100,000 light-years across. A civilization on the far side of the galaxy could be broadcasting right now, but their signals won't reach us for 100,000 years. We might be receiving signals from civilizations that went extinct millennia ago, their messages traveling through space long after the beings who sent them turned to dust. Or perhaps civilizations are beaming messages toward us right now, but those messages are still in transit, racing across the light years, and won't arrive for centuries or millennia. We might be early to the party, arriving before most of the guests. Here's something else that keeps astronomers up at night. What if we're receiving signals but we don't recognize them? We're looking for patterns that seem artificial, something that stands out against the random noise of the cosmos. But our definition of artificial is based on human technology. We look for narrow bandwidth radio signals because that's what our transmitters produce. We look for regular pulses because that's how we might send information. But an alien civilization might use compression algorithms, encryption, or error correction codes that make their signals look like random noise to our detectors. The most efficient way to transmit information is to make it as close to random as possible, minimizing redundancy. So the signature of an advanced civilization might be indistinguishable from cosmic static. When pulsars were first discovered in 1967 by Jocelyn Bell Burnell, they caused tremendous excitement. Here were radio sources producing regular pulses with extraordinary precision, some pulsing dozens of times per second with clockwork regularity. The Cambridge team that discovered them briefly wondered if they'd detected alien beacons. They even nicknamed the first pulsar LGM-1, standing for Little Green Men. But further observations revealed that pulsars are rapidly rotating neutron stars, the collapsed cores of massive stars left behind after supernova explosions. Their lighthouse-like beams sweep past Earth with each rotation, creating the observed pulses. Nature, it turns out, can create patterns that seem artificial. This taught astronomers an important lesson about jumping to conclusions. The challenge of recognizing intelligence brings up an interesting philosophical question. What exactly is intelligence, and would we know it if we saw it? We tend to define intelligence in human terms: problem-solving, tool use, abstract reasoning, language, technology. But those might be parochial definitions, limited by our own experience. Imagine an intelligent species that communicates through color changes in their skin, like cuttlefish do, but far more sophisticated. They might have rich inner lives, complex societies, and deep philosophical traditions, but they'd never invent radio because they communicate visually at close range. Or imagine a species with a completely different sense of time, one that thinks and acts over centuries rather than seconds. To them, we might appear to blink in and out of existence too quickly to notice, while to us, they'd seem like statues, unchanging and inanimate. There's also the question of collective intelligence versus individual intelligence. Ants aren't particularly smart individually, but an ant colony displays remarkably sophisticated behavior, building complex structures, farming fungi, waging wars, adapting to environmental changes. The colony functions as a superorganism with intelligence emerging from the interactions of millions of simple individuals. What if some alien intelligence works the same way? What if it's distributed across an entire planet's biosphere, with individual organisms acting as cells in a larger thinking system? We might be looking at it and not recognizing it as intelligent because it doesn't conform to our expectations. Some scientists have even speculated about the possibility of intelligence at much larger scales. Could a galaxy itself be intelligent? The idea sounds absurd at first, but consider that there are roughly 100 billion neurons in a human brain, and approximately 100 billion to 400 billion stars in the Milky Way. Neurons communicate through electrochemical signals. Stars and planetary systems are connected by gravitational interactions and potentially by electromagnetic fields and particles streaming through interstellar space. The timescales would be incomprehensibly slow from our perspective, with thoughts taking millions of years to form. But if such an intelligence existed, we'd be like bacteria living on a neuron, utterly unaware of the vast mind we're part of. It's wild speculation, but it reminds us that intelligence might exist in forms we've never imagined. Let's ground ourselves back in more conventional possibilities. One of the most pragmatic explanations for the Fermi paradox is simply that space is really, really big and detection is really, really hard. Our radio signals have only reached about 125 light-years into space. That's a sphere containing only about 15,000 stars, a tiny fraction of the galaxy's several hundred billion, and those signals get weaker as they travel, spreading out in all directions. By the time our strongest broadcasts reach even the nearest stars, they're incredibly faint, barely distinguishable from background noise. An alien civilization would need a radio telescope much larger and more sensitive than anything we've built to detect us from more than a few light years away. We've only been seriously searching for alien signals since 1960. That's just 66 years of observation, and for most of that time, with relatively limited technology. We've examined closely only a tiny fraction of the sky at a limited range of frequencies for a limited period of time. Imagine trying to find a specific person on Earth, but you're only allowed to look through a drinking straw, and you can only look for 1 second per day. The fact that you haven't found them doesn't mean they don't exist. It means your search has barely begun. The Breakthrough Listen project I mentioned earlier is helping to address this limitation. Over 10 years, it aims to survey 1 million nearby stars, scan the entire galactic plane and center, and observe 100 nearby galaxies. It's examining billions of radio channels simultaneously and looking at optical wavelengths too. If there are civilizations out there broadcasting at frequencies and power levels similar to what we use, and if they're within a few hundred light years, Breakthrough Listen should be able to detect them. But even this ambitious program has limitations. It can't detect civilizations that don't broadcast, that use frequencies we're not monitoring, or that are too far away for their signals to reach us with detectable strength. There's also the economic and political challenge. SETI receives minimal funding compared to other scientific endeavors. The entire budget for all SETI projects worldwide is less than the budget for a single large telescope. Most funding comes from private donors rather than governments. This makes sense from one perspective because the probability of success in any given year is low. But from another perspective, it's short-sighted. The discovery of alien intelligence would be arguably the most important scientific discovery in human history. It would answer one of our oldest and deepest questions. The potential payoff is enormous, even if the probability is small. Consider what would happen if we actually detected a signal. First, there would be an extensive verification process. Scientists would need to rule out natural sources, human-made interference, and equipment malfunction. Other observatories would need to confirm the detection. This process might take weeks or months. Once confirmed, the discovery would be announced, probably triggering the most intense media frenzy in history. every government, religious institution, and philosophical tradition would need to grapple with the implications. We're not alone. There are others out there. How would that change us? There are protocols in place for this eventuality. The International Academy of Astronautics developed a set of guidelines called the Declaration of Principles Concerning Activities Following the Detection of Extraterrestrial Intelligence. The declaration recommends that discoverers verify the signal, inform relevant authorities, and make the discovery public. It suggests that humanity should not reply until appropriate international consultations have taken place. Of course, there's no enforcement mechanism. These are guidelines, not laws. But they reflect an attempt to think through how we should respond as a species to contact. Would we reply? And if so, what would we say? This question has generated heated debate. Some scientists, including the late Stephen Hawking, warned against broadcasting our presence to the cosmos. Hawking argued that any civilization capable of reaching us would be far more advanced than we are, and history shows that when a technologically advanced civilization encounters a less advanced one, it usually doesn't end well for the latter. Columbus arriving in the Americas, Europeans colonizing Africa and Asia, these encounters often led to exploitation, disease, and destruction. Maybe advertising our location to potentially superior aliens is a terrible idea. Others argue that any civilization advanced enough to cross interstellar space would likely have resolved the internal conflicts and resource limitations that make our civilization dangerous. They'd be peaceful, cooperative, and curious rather than aggressive and exploitative. Otherwise, they would have destroyed themselves long before developing interstellar travel. This is a comforting thought, but it's also speculative. We simply don't know what an alien civilization's values or motivations would be. They might be completely alien in every sense of the word, operating according to logic and ethics we couldn't comprehend. There's also the argument that it's already too late to worry about this. We've been broadcasting radio and television signals into space for over a century. Those signals form an expanding sphere 125 light-years in radius, containing thousands of star systems. If anyone out there is listening, they already know we exist. Trying to hide now would be like closing the barn door after the horses have escaped. Though it's worth noting that most of our broadcasts aren't strong enough to be easily detected at interstellar distances. Only our most powerful military radars and deep space communication signals would stand out above the background noise. Some researchers advocate for active SETI, deliberately transmitting messages toward nearby stars in hopes of attracting attention. Several attempts have been made over the decades. In 1974, the Arecibo radio telescope in Puerto Rico transmitted a message toward the globular star cluster Messier 13, about 25,000 light-years away. The message contained information about mathematics, the elements, DNA structure, human form, and Earth's position in our solar system. It was more of a symbolic gesture than a serious attempt at communication, since any reply would take 50,000 years for the round trip. More recently, in 2017, a project called Messaging Extraterrestrial Intelligence transmitted messages to a nearby star called GJ273b. These efforts remain controversial within the scientific community. The content of our messages raises fascinating questions about communication across species and cultures. How do you create a message that an alien intelligence could understand? They wouldn't speak English or any human language. They might not even communicate acoustically. Their sensory systems could be completely different from ours. They might see in infrared or ultraviolet, hear ultrasonic frequencies, or perceive the world through electrical fields. They certainly wouldn't share our cultural references, our history, or our assumptions about meaning and symbolism. Most proposed messages rely on mathematics and physics, which we assume would be universal. The laws of physics are the same throughout the universe. A hydrogen atom in a distant galaxy has the same properties as a hydrogen atom here. So messages often start with basic mathematical concepts, prime numbers, simple arithmetic, geometric shapes. They might include information about atomic structure, our position in the galaxy relative to known pulsars, or the electromagnetic spectrum. The Voyager Golden Record included a diagram showing how to play the record and where Earth is located, all expressed in what the designers hoped would be universal scientific principles. But even these seemingly universal concepts might not translate. Our mathematics is based on assumptions about logic, quantity, and relationships that seem self-evident to us, but might not be to a truly alien mind. We assume that beings throughout the universe would discover the same mathematical truths we have. But what if mathematics itself is to some degree a human construction, a way of organizing reality that works for us but isn't the only way? What if aliens organize knowledge and understand the universe through completely different frameworks? These are deep questions that touch on the philosophy of mathematics and the nature of objective reality. Let's shift gears and talk about some of the more exotic solutions to the Fermi paradox. Some physicists have suggested that advanced civilizations might use technologies that make them invisible to us, not through intent, but through physics. For example, if a civilization harnesses energy from black holes or manipulates quantum fields in ways we haven't conceived, their activities might not produce detectable signatures in the frequencies and phenomena we monitor. They might communicate using neutrinos which barely interact with matter and pass through entire planets as if they weren't there. We're only beginning to develop neutrino detection technology. Or they might use entangled particles for instantaneous communication, bypassing the light speed limitation entirely, though our current understanding of quantum mechanics suggests this isn't possible for transmitting information. There's also the possibility that advanced civilizations don't use electromagnetic radiation for communication at all. They might manipulate space-time directly, creating gravitational waves that carry encoded information. We only detected gravitational waves for the first time in 2015, using incredibly sensitive instruments called LIGO that can detect changes in distance smaller than the width of a proton. Gravitational wave astronomy is in its infancy. We're not yet capable of detecting the kinds of patterns that might indicate artificial sources. An advanced civilization's communications might be washing over us right now, and we'd have no idea. Some theorists have even suggested that civilizations might transcend physical space entirely. If you can manipulate space-time, maybe you can create pocket universes, small regions of space-time that are disconnected from our own. An advanced civilization might retreat into such a pocket universe where they have complete control over the laws of physics, creating a customized reality perfectly suited to their needs. From our perspective, they would simply disappear, leaving behind perhaps a microscopic black hole or a tiny region of distorted space-time. All their technology, their culture, their billions or trillions of individuals would exist in a space smaller than an atom, undetectable and unreachable from our universe. This connects to ideas in theoretical physics about the multiverse. Many interpretations of quantum mechanics and solutions to cosmological equations suggest that our universe might be just one of many, possibly an infinite number of universes, each with potentially different physical laws. If travel between universes is possible, something we have no idea how to accomplish but can't rule out, then advanced civilizations might spread across the multiverse rather than across physical space within a single universe. They'd be exploring sideways through reality rather than outward through our cosmos. We'd never detect them because they're not here in our universe. These ideas venture into speculative territory, but they're worth considering because they highlight how limited our perspective might be. We're searching for aliens based on what we know, using the technology we have, looking for the kinds of signals we would send. But we might be like ants, trying to understand the internet. The phenomenon we're looking for might be all around us, operating at scales or through mechanisms we can't perceive or comprehend with our current understanding of reality. Now let me bring us back to something closer to home. One explanation for the silence that I find both hopeful and sobering is that civilizations simply have better things to do than expand across the galaxy. Think about what drives exploration and expansion in human history. We've explored and colonized new territories primarily for resources, living space, and sometimes fleeing danger or seeking freedom. But what if you live in a post-scarcity society where energy is abundant, matter can be rearranged at will, and you've solved the problems of disease, aging, and resource limitations? What motivates expansion then? An advanced civilization might focus inward on maximizing experience, knowledge, art, and personal fulfillment rather than outward on territorial expansion. They might spend their resources on creating sublime virtual realities, exploring the mathematical structures underlying reality, or achieving deeper states of consciousness. They might dedicate themselves to art, music, philosophy, and forms of experience we can't imagine. Physical expansion into space is expensive, slow, and dangerous. If you can achieve everything you want on or near your home world, why leave? This possibility suggests something profound about the nature of intelligence and purpose. We assume that expansion and growth are universal drives, that civilizations naturally want more territory, more resources, more power. But that assumption might reflect our evolutionary history and current limitations rather than a universal truth. We evolved as organisms that needed to compete for scarce resources. Expansion meant survival. But a civilization that transcends those limitations might also transcend the drive to expand. They might reach a state of equilibrium, content with what they have, focused on depth rather than breadth. If that's true, the galaxy might be home to many civilizations, each centered on their home star system, rich in culture and achievement, but with no interest in conquest or colonization. They'd be like houses in a suburban neighborhood, each with lights on and people inside, but nobody comes outside to socialize. Everyone stays home, absorbed in their own lives. From the outside, from our perspective, as the new arrivals, still learning how things work, the neighborhood looks empty and silent. We wonder where everyone is, not realizing they're all inside, living lives that don't involve wandering around the streets announcing their presence. There's also a deeply uncomfortable possibility that we need to confront honestly. What if intelligence itself is not an advantage on cosmic timescales? We tend to think of intelligence as evolution's crowning achievement, the trait that makes us special and successful. But from a purely biological perspective, intelligence is just one survival strategy among many. Bacteria have existed for over 3 billion years and will likely outlast us by billions more. They're simple, adaptable, and incredibly resilient. Beetles comprise about 25% of all known animal species. Ants collectively outweigh all humans on Earth. By measures of longevity, diversity, and biomass, these creatures are far more successful than we are. Intelligence, particularly the kind that leads to technology, might actually be a dead end in evolutionary terms. It allows a species to reshape its environment rapidly, but it also creates the capacity for self-destruction. Every intelligent species might face a bottleneck where their technological power outpaces their wisdom. They develop the means to alter their planet's climate, to engineer deadly pathogens, to create weapons of mass destruction, to build artificial intelligences they can't control, all before they develop the social structures, ethical frameworks, and foresight to manage these powers safely. Most species might not make it through this bottleneck. The galaxy might be littered with the ruins of civilizations that destroyed themselves within a few centuries of developing advanced technology. This is perhaps the darkest interpretation of the Great Filter. If it lies ahead of us rather than behind us, then the silence we hear is a warning. Every missing civilization is a cautionary tale. They reached for the stars and fell. They split the atom and couldn't put it back together. They changed their atmosphere and couldn't survive the consequences. They created thinking machines and lost control. The filter is merciless and nearly universal. Almost nobody gets through. If this is true, then our future hinges on whether we're wise enough, cooperative enough, and far-sighted enough to be one of the rare exceptions. But let's not dwell only in darkness. There are hopeful interpretations too. Perhaps the filter is behind us. Perhaps the jump from non-living chemistry to self-replicating life is so improbable that it's only happened a handful of times in the observable universe. Or perhaps the evolution of eukaryotic cells, cells with nuclei and complex internal structures, is the nearly impossible step. On Earth, this only happened once, about 2 billion years ago, when one simple cell engulfed another and they formed a symbiotic partnership. All complex life, every plant and animal and fungus, descends from that singular event. If that kind of merger is extraordinarily rare, then the universe might be full of bacterial worlds, but almost devoid of complex life. If the hard step is behind us, if we've already beaten the astronomical odds just by existing, then our future is more open. We might be one of the few civilizations to arise in this region of the galaxy, or even in the observable universe. That's a lonely thought, but it's also empowering. It means the future of intelligence in our corner of the cosmos depends on us. How we handle climate change, nuclear weapons, artificial intelligence, biotechnology, and social cohesion matters not just for our species, but potentially for life itself in this region of space. We might be the universe's chance to know itself, to create art and meaning, to light a candle against the darkness. No pressure, right? There's something else we need to consider, something that touches on the very nature of existence and consciousness. Physicist Enrico Fermi asked where everybody is, but implicit in that question is an assumption that everybody means something like us, beings made of matter, living in three-dimensional space, experiencing time in a linear fashion. But what if consciousness, intelligence, and life can exist in forms that don't fit that description at all? What if the universe is teeming with intelligence, but it exists in higher dimensions we can't access, or in quantum superpositions we can't observe, or as patterns in dark matter we can't detect? Dark matter comprises about 85% of all matter in the universe, yet we can't see it or touch it. It doesn't interact with electromagnetic radiation. We only know it exists because of its gravitational effects on visible matter. What if dark matter isn't just inert stuff but can organize into complex structures? What if there are entire civilizations made of dark matter, living in the same space we occupy but unable to interact with us except through gravity? They'd be ghosts, invisible and intangible, sharing our galaxy but forever separate. It sounds like science fiction, but the universe has surprised us before with phenomena stranger than anything we imagined. Let me share something that gives me hope despite all the uncertainty. The search itself, the act of looking and wondering, reveals something beautiful about humanity. We're a species that looks up at the stars and asks questions. We build instruments to extend our senses across cosmic distances. We dedicate our lives to understanding the universe even when it doesn't offer immediate practical benefits. That curiosity, that drive to know, might be our most important characteristic. Whether or not we ever find alien intelligence, the search makes us better. It forces us to think about our place in the cosmos, to confront our assumptions, to imagine possibilities beyond our everyday experience. Every exoplanet we discover expands our understanding of how planetary systems form and evolve. Every star we study teaches us about stellar physics and the life cycles of stars. Every signal we analyze, even if it turns out to be natural or human-made, improves our technology and methodology. SETI research has driven innovations in signal processing, data analysis, and radio astronomy that have applications far beyond the search for aliens. The Allen Telescope Array in California, built partially for SETI research, also contributes to our understanding of cosmic phenomena like pulsars, black holes, and the evolution of galaxies. Moreover, thinking about alien life forces us to think about life itself in deeper ways. What is life? How do we define it? On Earth, all life shares common characteristics: metabolism, growth, reproduction, response to stimuli, evolution through natural selection. But are these requirements universal? What about viruses which reproduce but don't metabolize? What about computer programs that evolve and compete for resources? What about prions, misfolded proteins that can replicate their shape in other proteins, causing disease? These edge cases on Earth hint at the possibility that life elsewhere might be even stranger, operating according to principles we've never encountered. Astrobiologists are now thinking about weird life, hypothetical organisms, that might use different chemistry than Earth life. All life on Earth uses water as a solvent, but could life use liquid methane, like in the lakes on Saturn's moon Titan? Could it use ammonia or sulfuric acid? Earth life is carbon-based, using carbon's ability to form long chains and complex molecules. But silicon has similar properties. Could there be silicon-based life? Most biochemists are skeptical because silicon-oxygen bonds are very stable, making it hard for silicon to form the dynamic, changeable molecules that life requires. But we shouldn't rule it out entirely. The universe might be more creative than our theories allow. There's a concept in biology called convergent evolution. When organisms face similar environmental challenges, they often evolve similar solutions independently. Wings evolved separately in insects, birds, bats, and pterosaurs. Eyes evolved independently dozens of times. This suggests that certain solutions to survival problems are so effective that evolution finds them repeatedly. Some scientists think intelligence might be convergent too. If true, then wherever life becomes complex, intelligence might eventually emerge because it's such a useful adaptation. This would make intelligent aliens more likely, which deepens the Fermi paradox. If intelligence is a convergent solution, why don't we see evidence of it everywhere? But convergent evolution also teaches us something else. While the general solution might be similar, the details are always different. Bird wings and bat wings both enable flight, but they're constructed differently, evolved from different ancestors, and work in somewhat different ways. If intelligence is convergent, alien intelligence might be similar to ours in some abstract sense, the ability to model reality, solve problems, and communicate complex ideas, but radically different in implementation. Their brains might use different neural architectures, process information at different speeds, or integrate senses we don't possess. Understanding them might be less like learning a foreign language and more like trying to communicate with an artificial intelligence, something that shares some cognitive capabilities but operates according to fundamentally different principles. This brings me to one of the most intriguing modern developments in the search for alien life, the study of technosignatures. While biosignatures are chemical signs of life, technosignatures are signs of technology. We've already discussed some of these like radio signals and megastructures, but researchers are getting more creative about what to look for. For example, industrial pollution. Our own atmosphere now contains chemicals that don't occur naturally, chlorofluorocarbons from refrigerants, nitrogen compounds from fertilizers, and various industrial byproducts. These chemicals have distinctive spectral signatures. If we can detect them in an exoplanet's atmosphere, it would suggest industrial activity. Another technosignature would be artificial lighting. Our planet glows at night with billions of electric lights. From a distant vantage point, this would be detectable, especially on the dark side of Earth as it rotates. An alien observer with a sensitive enough telescope could see the lights of our cities. We might be able to do the same, looking for planets that show illumination on their night sides that can't be explained by reflected starlight or natural phenomena. The James Webb Space Telescope isn't quite sensitive enough for this yet, but future instruments might be. Some researchers are looking for signs of solar panel arrays. If a civilization covers significant portions of their planet with solar panels to harvest energy, it would change the planet's reflectance spectrum in detectable ways. Solar panels absorb visible light but reflect infrared, creating a distinctive signature. Others are looking for heat signatures. The laws of thermodynamics tell us that any energy use eventually produces waste heat. A civilization using vast amounts of energy would make their planet or their star system, if they've built megastructures, warmer than it should be based on the star's output alone. We could detect this as excess infrared radiation. There's even discussion about looking for atmospheric engineering. If a civilization is terraforming planets, perhaps pumping oxygen into Mars-like atmospheres to make them habitable, or removing carbon dioxide from Venus-like atmospheres, we might detect atmospheres that are obviously out of equilibrium with their planet's geology and stellar environment. These would be smoking guns, signs that someone is deliberately modifying a world. The possibilities are limited only by our imagination and our technology's sensitivity. One of the most ambitious proposals is called the World Ship Hypothesis. Instead of looking for civilizations on planets, maybe we should look for civilizations in space. Generation ships, enormous vessels that contain entire ecosystems and populations, might be more common than planetary civilizations. After all, planets are at the bottom of deep gravity wells. Launching from a planet requires enormous energy. But if you're born in space, in a rotating habitat with artificial gravity, you never face that limitation. You can harvest materials from asteroids, energy from the sun, and build whatever you need. Space-based civilizations might be the norm for advanced species, with planet dwellers like us being the cosmic equivalent of tribes that never left their ancestral village. If that's true, we should be looking for mobile structures in space, habitats that might be traveling between star systems, or settled in stable orbits around stars. They might reflect light in unusual ways or emit heat signatures that don't match natural objects. The challenge is that space is vast and these objects would be small compared to planets. Finding them would be like searching for needles in an infinite haystack. But as our survey capabilities improve, particularly with upcoming space telescopes like the Nancy Grace Roman Space Telescope and the proposed LUVOIR mission, we'll be able to search larger volumes of space with greater sensitivity. Let's talk about the practical implications if we actually do find evidence of alien life or intelligence. The impact would depend enormously on what we find. If we detect biosignatures on a planet 40 light-years away, it would be profound scientifically, but might not immediately change daily life for most people. We'd know we're not alone, but we couldn't communicate or interact with organisms that are effectively separated from us by an uncrossable gulf. It would be like looking through a window into another world, able to observe but never to touch. If we receive a signal, an intentional message from an alien civilization, the impact would be more immediate and dramatic. First would come the verification process. Is it really artificial? Where exactly is it coming from? What is it saying? Teams of cryptographers, linguists, mathematicians, and scientists would work to decode the message. This might take years or decades depending on how the message is structured. Meanwhile, the world would be transformed by the knowledge that intelligent aliens exist and are trying to communicate. Religious institutions would need to reconcile the discovery with their teachings. Most major religions don't explicitly address the possibility of alien life, though some theologians have thought about it. In Catholicism, for example, some scholars have argued that God's creation could include other rational beings and Christ's redemption might apply to them in ways we don't understand. Other religious traditions might find it easier or harder to accommodate the discovery. There would certainly be intense theological debate and, for some people, a crisis of faith. Politically, the discovery might unify humanity or divide us further. Some optimists hope that contact with aliens would make our earthly differences seem petty, bringing nations together in common purpose. We'd think of ourselves as earthlings first, humans representing our planet to the cosmos. But it's equally possible that nations would compete for advantage in any contact scenario, fighting over who gets to reply, what message to send, or how to interpret the aliens' intentions. The United Nations has an Office for Outer Space Affairs that would probably coordinate international responses, but it has limited authority. Economically, the discovery might trigger a new space race. Nations and private companies might pour resources into space technology, hoping to establish communication or eventually make contact. We'd see massive investment in propulsion systems, life support, artificial intelligence, and other technologies relevant to interstellar communication or travel. This could accelerate technological development dramatically, similar to how the original space race drove innovation in computing, materials science, and telecommunications. Or it might drain resources from addressing problems here on Earth, a cosmic distraction from terrestrial challenges. Psychologically and culturally, the impact would be profound. Humanity has never had a mirror to see ourselves reflected in another intelligent species. We'd be forced to recognize that human intelligence, human consciousness, human culture, all the things we consider uniquely special about ourselves, are actually just one example among many. This could be humbling or inspiring, depending on your perspective. Artists, writers, musicians, and philosophers would find endless inspiration in contemplating the alien other. We'd see an explosion of cultural production trying to make sense of our new place in the cosmos. But here's what I think would be the most important consequence. It would change what seems possible. Right now, interstellar travel, building civilizations among the stars, surviving as a species for millions of years, these all seem like distant, maybe impossible dreams. But if we knew for certain that another species had done it, that they'd overcome the challenges and created a lasting civilization, it would prove it's possible. We'd have an existence proof. If they did it, we could too. That knowledge might be exactly what we need to commit ourselves to the long-term project of becoming a spacefaring civilization, to think in terms of centuries and millennia rather than quarters and election cycles. Conversely, if we eventually conduct a thorough search and find nothing, that would also be profoundly meaningful. It would suggest that intelligent life is incredibly rare, that we might be alone or nearly alone in the observable universe. That realization would make Earth infinitely precious. We'd understand that consciousness, the ability to appreciate beauty, to create art, to love and wonder, and ask questions about existence, might be the rarest phenomenon in the cosmos. Every species on Earth, every ecosystem, every human culture would become sacred because they might represent something that barely exists anywhere else. The stakes of our choices would become cosmically high. If we destroy ourselves or our biosphere, we might be extinguishing something irreplaceable on a galactic or even universal scale. I often think about what future generations will know that we don't. 1,000 years from now, or 10,000, will humanity have answered the Fermi paradox? Will our descendants look back and smile at our uncertainty, the way we smile at medieval debates about whether the Earth is the center of the universe? Will they live in a galaxy teeming with civilizations, trading messages and ideas across the light years? Or will they look out at the same silent cosmos we see, carrying the lonely torch of consciousness through an empty universe? We don't know. And maybe that's appropriate. The question is so profound that perhaps each generation needs to grapple with it anew, bringing fresh perspectives and technologies to bear on the mystery. What we can do is keep searching, keep building better instruments, keep thinking more creatively about what to look for and where to look. We can also focus on becoming the kind of civilization that would be worth finding. If there are aliens out there watching us, what would we want them to see? A species that comes together to solve problems, that values truth and beauty, that treats its homeworld and fellow creatures with care, that reaches for the stars not with weapons, but with open hands. The Fermi paradox ultimately asks us to think about intelligence, life, purpose, and existence at the largest possible scale. It connects astronomy and biology, physics and philosophy, technology and ethics. It forces us to examine our assumptions about what's normal, what's possible, and what matters. Every answer we propose reveals something about how we see ourselves and our place in the cosmos. Maybe we're alone, maybe we're early, maybe we're surrounded by civilizations we can't detect. Maybe the universe is young and we're among the first. Maybe it's old and we're among the last. Maybe intelligence is common but brief. Maybe it's rare but enduring. Maybe space is too vast, time too long, technology too different. Maybe they're here already, watching and waiting. Maybe they were here long ago and left. Maybe they'll arrive tomorrow, or in 1,000,000 years. Maybe the question itself is flawed, based on assumptions that don't apply to truly alien intelligence. What I can tell you with certainty is that the search has value regardless of what we find. It expands our knowledge, drives technological innovation, and most importantly, it keeps us asking one of the deepest questions possible. Are we alone? In asking that question, we're really asking, what are we? What is consciousness? What is our responsibility to life and intelligence in the universe? These questions don't have easy answers, but wrestling with them makes us more thoughtful, more humble, and more aware of how precious and strange our existence is. So when you look up at the night sky, remember that you're seeing hundreds or thousands of stars, each potentially hosting planets, and each of those planets might harbor life. The atoms in your body were forged in ancient stars that exploded billions of years ago. You are literally made of stardust, as is everything around you. The universe has arranged itself into patterns complex enough to wonder about the universe. You are the cosmos contemplating itself. Whether you're the only such arrangement in the observable universe or one of countless trillions, that fact remains staggering and beautiful. The Fermi paradox remains unsolved. Where is everybody? We don't know yet. But in searching for the answer, we're engaged in one of the most profound adventures in human history. We're reaching out into the darkness, hoping for an answering light. We're asking if intelligence and consciousness exist elsewhere, if meaning and purpose extend beyond our small world. And perhaps most importantly, we're deciding what kind of civilization we want to be, because the answer to where is everybody might someday be right here. We made it. We survived. We became the aliens that future civilizations will search for. The universe is 13.8 billion years old. It will likely continue for trillions of years more. We've been searching for alien intelligence for less than a single human lifetime. The story is just beginning. What happens next depends partly on what's out there, but it also depends on us, on whether we survive our challenges, whether we keep looking, whether we remain curious and hopeful. The silence we hear from the cosmos is not yet a final answer. It's an invitation to keep asking, keep searching, and keep wondering. And maybe someday, whether in our lifetimes or in the lifetimes of our distant descendants, that silence will break. Someone will receive a signal that can't be explained away. We'll know, finally and forever, that we're not alone. Until then, we keep searching, we keep hoping, and we keep being the kind of species worth finding. That's where we are with the Fermi paradox. It's a question without an answer, a mystery that might be solved tomorrow or remain unsolved for millennia. But It's our mystery, our question to pursue, and there's something beautiful about that uncertainty, that possibility that the next discovery could change everything we think we know about life, intelligence, and our place among the stars. If you made this far, I am sure you will love this other video at the left side of the screen. The true scale of the universe, why your brain can't comprehend how big it really is. In this video, we explore why your brain can't comprehend how astronomically vast the universe truly is, and we will explore how understanding the cosmic scale reveals about your existence in the cosmos. See you there.